Hi, my name is Pablo Picazo and I'm going to talk about how Chromium-based browsers handle the security and privacy of users by using a file called Secure Preferences. Before I start with more technical details, let me show you what Chromium-based browsers are, as well as some of the most common examples of browsers based on it. Chromium is an open source browser developed by Google around 2008. Since then, many vendors have used it as a basis for building their own browsers. Some examples are Opera, Google Chrome, Brave, and Microsoft, who was the last one to use Chromium for their new browser called Edge. According to StatCounter, a web page that measures the market share of the browsers, if we sum up all the users of these four browsers, we might easily get 80% of the total desktop users on the internet. Therefore, guaranteeing the security of these browsers is of extreme importance, since any vulnerability will affect many users all around the world of many browsers. There are some settings we can directly change from the browser. This is done through an internal web page called Chrome Settings. Among many other options, we can change the search engine, which web page or web pages the browser should automatically open when we open a new instance, the web pages that have to be open when we open a new tab. We can show or hide the home button or even managing the bookmarks toolbar. Apart from this, we can also manage browser extensions on another internal web page called Chrome Extensions. Here, we can install, uninstall, enable, disable extensions, and even modify some of the options of them individually. Extensions are small pieces of software that run in the browser context and can access to almost all the content the user sees. Apart from this, extensions can use some of the privileged APIs the browser exposes. So, for instance, they can have access to cookies, the history of the user, or they can even modify other extensions. As an example, here we can see Google Translate extension that when the user clicks on the icon located on the toolbar, it starts the Google Translate extension. As I said previously, the user can also modify the settings of the extensions individually. So, for instance, in the case of the Google Translate, we can define the scope of the extensions, which set of web pages this extension is executed on, but we can also allow this extension to be executed in incognito mode, or allow the execution of the extension in HTML files that we have locally stored in our computer. Because of security issues, Google banned years ago the installation of browser extensions from sources different than the official ones. Even though most of the vendors have their own web store, like the Google Web Store, Opera add-ons, or the one provided by Microsoft, the majority of the browsers accept browser extensions coming from the Google Web Store. The reason is basically because all these browsers are based on Chromium and that the source code is shared among them all. Okay, so now that we are all on the same page, the question is where all this information is stored. And the answer is that everything is stored in a local file called Secure Preferences file. This is a JSON file that has all the settings of the user as well as internal configuration of the browser. The browser automatically loads all the settings stored in the file each time we open it, and when we close it, the browser keeps track of the changes, if any, and stores them in the file. Here we can see some options like showing the home button, how the home page is defined, the search engine we have as default, as well as the extensions we have installed, and how they are stored in the preferences file. If we expand the extensions part, here we can see how the information that this file stores of the extension called Hangsout. Among other things, we can see when the extension was installed, if it's enabled or disabled, the manifest, and where the extension is stored in the file system. Google realized in 2012, some years ago after launching the browser, that this freely modification of the secure preferences file might have potentially security issues. So they introduced a security mechanism such that the browser is the only one that can modify that file. This mechanism is known by HMAC. So the HMAC is basically a hash function computed from two values, a message and a randomly generated key or seed. And how is this implemented in Chromium? Well, this HMAC is computed from a seed stored in a file called resources.pag, while the message is a string composed of some parts of the secure preferences file. And also, depending on the operating system the user is, it might also have a prefix like the Windows SID. The browser computes all the HMACs of the secure preferences each time we close the browser, and it checks the integrity of the file each time we open a new instance of it. If the HMACs don't match, then the browser detects that the file is corrupted and restarts it to a previous state. Apart from that, it also warns the user that the file has been corrupted. More concretely, the HMACs are stored in a key of the secure preferences file called MAC and then another one called protection. In this example, we can see the HMAC of basically the same options like we saw previously, like the home button and the search engine. In the following, we are going to see each one of the parts individually so we can understand how both the seed and the message are obtained in more detail. Well, as I said before, the seed is stored in a file called resources.pag. This file is provided by the browser, and it has different content depending on the vendor and the operating system the user has. Here we can see the usual paths that this file has in different platforms. For instance, in Chrome, it has the blank string in both Mac and Linux, whereas in Windows, the seed looks like the string we can see at the right part of the screen. Similarly, we can see how Brave, Edge, and Opera just use the blank string everywhere. We extracted the seed multiple times on different platforms and we got the same seed every time. So once we know that the seed is somehow fixed, let's see what happened to the message. The message is basically composed of two main parts, a prefix and the content of the secure preferences file we want to modify. The prefix depends on the platform the user has. For instance, in the case of Windows, the prefix is the SID without the last 4 digits that basically correspond to the relative ID. In the case of Mac, the prefix is the UUID of the hard disk, the main one, whereas in the case of Linux, there is no prefix at all. Actually, this method is not even implemented in Chromium source code. We also include some of the examples of the statements that we use to retrieve these values in both Windows and Linux. The other part of the message comes directly from the secure preferences file. It's basically the path of the keys of the JSON plus the values we want to change between quotes. The path follows the dot notation. So, for instance, if we would want to show the home button of the browser, which is under the browser key, as we can see in the slide, the part of the message corresponding to the secure preferences file will look like the example at the bottom. That is browser.showHomeButton and the value which is true between quotes. If we put all together the prefix and the properties we want to change, here we have some examples depending on the platform. We are Concretely, we are setting the web page of the conference at the home page of the user. Finally, once we know how to create the message, and assuming that the seed is fixed as we already saw, we have to compute the HMAC function using both the message and the seed. To do so, Chromium uses a SHA-256 hash function. But this is not all. Chromium also introduced one more security check to somehow guarantee the integrity of the file. They call this SuperMAC, and it has the same structure as before, but in this case the message is composed of the whole max entry of the secure preferences file, including the previous SuperMAC that we computed. After that, we have to compute once again the HMAC, and it's stored in the new SuperMAC. So with this, we are not able to bypass the security mechanism implemented by Google years ago and freely modify the secure preferences file, thus impersonating the browser. We could not only change the property of the browser, like importing bookmarks from files, but also changing any of the configuration of the browser extensions. From the security point of view, this is quite risky. We will be able to install, uninstall, enable, disable, add new permissions to malicious extensions, delete some of them, expose all the content of the extension to web pages, etc. We also want to emphasize that we made all the source code we use for the experiments available on GitHub. Okay, so once we know how Chromium generates the HMAC and how it modifies the secure preferences file, there is at least one more question we have to answer, which is this security issue already being exploited in the wild? Is there any software out there modifying the secure preferences file without having to do so? Well, I think many people will remember this installation process, which basically belongs to Java, and at some point, if the user is not aware of the installation and is just clicking on the accept button and doesn't manually uncheck the checkbox, it automatically changes the home page, the search engine, as well as the web page when a new tab is opened. This is known as a potentially unwanted programs, and we know that this is quite old, and since then, many antivirus vendors as well as operating systems have implemented clever countermeasures to fight against this unwanted software. So someone might think that this is not possible anymore. We, of course, analyzed all of our scripts and all the software we use for modifying the secure preferences file, and none of them were marked as malicious by any antivirus vendors, nor any of the operating systems that we used. So, having said that, is there any current software abusing of this vulnerability nowadays? Well, yes, it is. We found one, which is, in this case, we are now seeing the installation process of uTorrent, and similar to the previous example, at some point during the installation, it tries to cheat the user by offering the installation of a browser extension. If the user, as before, doesn't explicitly decline that, the McAfee Web Advisor browser extension is automatically installed in Chrome. So, okay, now that we have seen some old and current examples, there is something else we have to have in mind, which is like, someone might think that, okay, if we don't have browser extensions, perhaps we are kind of safe. But this is not true. When we install a new Chromium-based browser, it comes with a bunch of functionality implemented, and some of this functionality comes in the form of browser extensions. This is known as install by default extensions, and each vendor implements its own set of installed extensions, installed by default extensions. So for instance, Brave comes with 10 extensions where only 3 of them can be disabled. Chrome comes with 16 where only 7 can be uninstalled. Edge comes with 11 and no one can be either installed or disabled or uninstalled. And finally, Opera comes with 21 already implemented extensions where only 1 can be disabled. So what does this mean? How an attacker can get any advantage of these installed by default extensions? Okay, so let's take a look at the Hangsout extension to see what the implications are and what an attacker can do by modifying this secure preferences file. So here we have the manifest file of the Hangsout extension. This file is the only mandatory one that all browser extensions have to define. In it, developers declare the configuration of the extension, so for instance, which permissions are needed, the background pages, the content scripts, which resources are exposed to web pages, and which web pages can send messages directly to the extension. These are just a few examples, but of course there are many other parameters that can be configured. In particular, we will use the externally connectable key as a vehicle to exploit one of the installed by default extensions, to exploit this Hangsout extension. The externally connectable key declares which extensions, apps, and web pages can connect to your extension via JavaScript methods like runtime connect and runtime send message. This is the definition provided by Google. So in this case, by looking at the Hangsout extension, we can see how in the matches property of the externally connectable key, there is a pattern defined, which basically means that any web page under the Google domain can send messages directly to the extension. So here we have an example of a JavaScript source code similar to what Google might have to retrieve information about the user, like the GPU usage or the network performance, among many other parameters. This is done basically by creating or by using this runtime connect and using as a parameter a string called process CPU. But also, Hangsout, this extension accepts another option as a parameter, which is choose desktop media. And by using this other option, Google can have access to the screen of the user. For instance, get screenshots of the window as well as the tab of the browser and also the mic of the user. So what happens if an attacker would inject another domain or a web page under her control, let's say attacker.com, into the matches list of the externally connectable key of that extension? Well, then when the user visits the attacker webpage, all the previous information and all the media that we saw can also be retrieved by the attacker. So if the attacker combines this modification with any other, like including her web page as the home button, as the home page, or including the web page, the attacker web page as pinned tabs, or including the web page as part of the bookmarks, it will try to cheat the user and increase the probability of being success in the attack. In addition to that, it's also important to remember that this extension is an install by default one, so users cannot get rid of it, and therefore the attack will be basically valid until the secure preferences file is restored.
As a conclusion, we want to remark that even though Google banned years ago the freely modification of the secure preferences file, Much more effort needs to be done to protect the security and the privacy of users on the internet. Of course, we informed and provided with all the details and the source code we use in our experiment to the main vendors, and hopefully they will come up with a solution for this. Thank you so much.